Scientists are supposed to be the most objective among us. It's one of the reasons academic publications are usually written in third person. Using I or we might suggest that people were involved and brought their own biases into the study. But scientists are, in fact, people. And despite how hard they work to reduce the influence of their own perspectives, their lives shape their research. Sometimes they become scientists because of those experiences. For example, trauma could open their eyes to a neglected area of research, or an unexpected diagnosis might inspire them to look into a rare disease that no one else is going to study. As it turns out, science isn't as impartial as some people like to think, and that's a good thing. Just ask these 5 scientists who are finding treatments for their own diagnoses. In 2010, David Fajgenbaum was training to be a medical doctor. He was looking forward to a life of helping other people when they got sick, until his own health went downhill fast. He had overwhelming fatigue and enlarged lymph nodes that told him something was very wrong. As it turned out, his organs were failing. Suddenly, he needed to use his medical training to save himself. In the prime of his life, he found himself in the hospital literally on the brink of death at least 4 times in 3 years. Nobody knew what was causing his body to fail, but eventually he got his diagnosis: Castleman disease. It's a rare immune disease that attacks your organs, but his version was even rarer. Fajgenbaum was diagnosed with idiopathic multicentric Castleman disease, a very specific problem that is very dangerous for very few people in the world. The leading experts on that disease at the time were studying in Arkansas, so he booked a trip there. And none of them knew how his particular subtype worked, which meant he had to figure it out himself. Since any good investigation needs data, he started by gathering blood samples to analyze. Specifically, he gathered his own blood samples that had been taken during those years in and out of the hospital, and he started running tests. The results pointed to a specific enzyme that's supposed to help you make proteins, grow cells, and regulate your metabolism. It's called mTOR, and it was in overdrive. This was a huge discovery because once he knew that mTOR was overwhelming his blood samples, Fajgenbaum could look for ways to bring it back down to healthy levels, like by taking a drug that already exists. Sirolimus, also called rapamycin, is an mTOR inhibitor used to prevent people's bodies from rejecting new organ transplants, among other things. Considering how long it takes to create a new drug and get that into production, Fajgenbaum's chances for a long, healthy life would be increased dramatically if this drug got his Castleman disease in check. So he convinced his primary care physician to try using sirolimus for a purpose that it was not developed for. And it worked. More than a decade later, he's still in remission. After that success, he wanted to do what he could for other people in the same situation. That's when he opened his own research lab focused on Castleman disease. In 2020, his lab published an analysis of the lymph nodes of people with the idiopathic multicentric version of the disease. They found that they also had more mTOR than usual, so he's not a unique case. At the time we're filming this video, a phase 2 clinical trial is being conducted to see if mTOR drugs can effectively treat more people with Castleman disease. And Fajgenbaum's research reveals similar trends for patients with diagnoses that have a lot in common with Castleman disease. Fajgenbaum might have started out trying to save his own life, but he ended up founding multiple nonprofits to find other already approved drugs that may treat rare diseases. In the last few years, they've advanced 14 drugs to be repurposed as treatments for diseases like Castleman. Today, thousands of lives have been saved, including his own, from this work. And the stakes are just as high for our next scientist on our list. Chris Nowinski was just a normal guy following the same old boring career path that most of us do. He played football at Harvard, graduated to be a professional WWE wrestler, became a published author, and finally, a neuroscientist. See, during his time with WWE, he got kicked in the chin hard enough to give him a concussion and end his wrestling career. He had temporary amnesia after impact, then would get throbbing headaches whenever his heart rate went up, and eventually developed a sleep condition. That kind of injury can change an athlete's life. For Nowinski, it inspired him to dedicate himself to head trauma. First, he spread the word in a book about football players with concussions, which he knew about from his time playing football. Then, he got a PhD in behavioral neuroscience from Boston University. He wanted to study the brains of athletes who had experienced head trauma, but brains are hard to come by, and the process of acquiring them was intense. He individually called medical examiners and the families of each deceased head trauma victim that he wanted to study, and he asked for their permission. To give you an idea of how hard that was, on top of the emotional toll it took, he was met by medical examiners that didn't believe what he was investigating was a real disease. These days, we know it as chronic traumatic encephalopathy, or CTE. But back then, it wasn't nearly as well understood. We didn't know all of CTE's wide-ranging symptoms, from less control over your impulses, to depression, to progressive dementia. And we definitely didn't know how multiple subconcussive hits can have similar effects to those big hits that immediately throw you off. After all, you can move on from them relatively quickly and think you're fine, and the effects might not appear for decades, so they don't always get attributed to the impact. But with the help of the Concussion and CTE Foundation, Brain Bank, and Brain Donation Registry that Nowinski started, researchers got a lot more data, and we're learning how common this problem is. After those initiatives, many athletes publicly pledged their brains to research. So Nowinski no longer had to gather them one by one, and he could contribute to a 2024 study that analyzed hundreds of them. That study found some serious effects of traumatic brain injury. Basically, these brains were thinner with fewer brain cells, and it got worse the longer brain donors had played contact sports. In this dataset, CTE donor brains were wasted away in critical areas, like where you store memories. It's the kind of brain thinning seen in dementia, and a protein that's often less present among dementia patients was showing the same trend in these CTE brains. So CTE is seriously damaging people's brains. But we're moving in the right direction. In addition to his research, the publicity that Nowinski stirred up around CTE has led to changes in the rules of some sports. Like, heads are much more off-limits in American football than they used to be. There's still a lot that needs to happen if we want to seriously reduce head trauma, but the first step was getting it on people's radar. Medical research certainly wasn't on Sonia Vallabh's radar. She went to law school. Ask any lawyer. You don't do that for fun. You do it because then you get to work in a field at least a little related to law, like more related than running a biomedical research lab. But sometimes life takes you in directions you never expected. For Vallabh, this drastic career change started when her mom fell ill. She lost weight, her vision, and her memory. And at age 51, Vallabh's mother was dead. Without many clues, the whole thing was a mystery, so the family opted for an autopsy, and the results would change their lives forever. Sonia Vallabh's mother had died of a Prion disease. These occur when a misfolded protein in the brain causes other proteins to malfunction, spreading through your brain and killing your neurons. These diseases ramp up in a matter of months, degrade your brain, and without a doubt will kill you. They might even kill your whole family. See, Vallabh's Prion disease was genetic. 1 in 50,000 people has this single-letter DNA mutation in their prion protein gene, PRNP, and they can pass it down to their children, meaning Sonia Vallabh had a 50% chance of inheriting it from her mother. And one test later, she learned that she had the mutation too. Vallabh knew that there was no cure, meaning this prion disease would kill her if nothing changed. So she rolled up her sleeves and got to work. She and her husband left their careers, earned PhDs in biomedical science, and opened their own lab devoted to studying prion diseases. The rogue prion protein they study is called PRP. It's the one that misfolds and causes the deadly effects I talked about earlier. Usually, PRP helps your nerves send signals by maintaining their myelin coating. But when it changes shape, it becomes a prion and causes disease. PRP is necessary for prion disease, but we know that mice can live a healthy life without PRP. So in Vallabh's lab, they're working on a treatment that would reduce PRP before it goes rogue. That way, you have less fuel around when the fire breaks out. As a person who knows she has the genetic mutation, but hasn't entered disease progression yet, Vallabh thinks about the problem differently from other researchers. She's not waiting until symptoms start to treat them. She's looking for more preventative options that keep disease from starting at all. And her search is paying off. She has demonstrated that this approach can work against prion diseases in mice. You don't even have to 100% eradicate PRP to get an effective prophylactic. Just reducing it by 21% helped prion-infected mice live longer. And it only took 1 week of treatment to cut PRP RNA in half. So that goal seems very attainable. Plus, the mice that had started showing symptoms benefited too. After a single treatment, mice lived longer than their untreated peers and reversed some of their weight loss. Some mice even reversed signs of brain damage. It's definitely not a cure yet, But this treatment idea seems to improve longevity and quality of life. For terminal diagnosis, early intervention options that delay the start of the disease and give you back some of your life are huge. For now, the data comes from mice, but there are several clinical trials currently underway, which Vallabh and her husband built the infrastructure for. And Vallabh is optimistic that this will be a real treatment option for people like herself within the next few years. In these situations, many doctors find genetic testing hopeless, because there's no cure. But Vallabh encourages people to seek genetic testing and join trials to make progress toward treatment. From her perspective, knowledge is empowering and might even change her fate. Before we introduce the next incredible scientist working on their own diagnosis, it's time for a quick ad break.
Thanks to 80,000 Hours for supporting this SciShow video. As a nonprofit, their only aim is to help you find a fulfilling, high-impact career. And we at SciShow love a nonprofit. If you're worried about AI automation, 80,000 Hours is too. They've just released a new edition of their career guide, 80,000 Hours, How to Have a Fulfilling Career That Does Good. It explains how to plan a meaningful career in the age of AI. With tools like that and a job board with hundreds of hand-picked roles updated daily, 80,000 Hours can help you work towards solving our most pressing problems. On average, you'll spend 80,000 hours in your career. So here's how you can try to spend that time well. Go to 80,000hours.org/SciShow or click the link in the description or pinned comment to pre-order your copy of their updated career guide. Learn what makes a high-impact career, get new ideas for impactful paths, make a new plan based on what you've learned, and put it into action.
Julio Saez-Rodriguez was a scientist long before he became a patient. He spent his life researching the molecular basis of disease, but when he was diagnosed with a terrible one himself, he had never even heard of the condition. This was even more surprising once he started looking into the disease. It's the reason for 1/3 of all adult kidney transplants. It affects a lot of people, and without treatment, it can be deadly. It's called IgAN. IgA stands for immunoglobulin A, the main antibody in your gooey bits, saliva, tears, that kind of stuff. So it's normally a good thing to have around. But when it gets into your kidneys, it can spark chronic inflammation, eventually leading to end-stage kidney disease, aka nephropathy. That's the N in IgAN. When Saez-Rodriguez was diagnosed more than a decade ago, he didn't have many options to treat his IgAN. But considering his background in bioinformatics, he had the tools to look into it. It just didn't occur to him to study something like IgAN until that point, because his own research was just following the field. And that meant pretty much ignoring kidney problems, because that's not where the money is, despite it being a major killer. But his new perspective as a patient changed that. He realized that IgAN is actually a great candidate for investigation through the big data approaches that he specializes in. For example, Saez-Rodriguez created a new tool to make sense of giant datasets holding information about your genes. The idea was to use different sources of things we know, like how proteins interact with each other, to see where those different sources overlap and result in disease. Through this analysis, Saez-Rodriguez and his team were able to identify 20 molecules in the body that play a role in IgAN. And when we know those molecules are involved, we can do something about them. There are drugs that already exist that act on those molecules, but those drugs haven't been applied to IgAN yet. So the solution might be out there already. It's like what Fajgenbaum is doing to find drugs that could be used in new ways instead of making new ones from scratch. With 20 target molecules, there's potential for a variety of drugs to help people who have different experiences with IgAN. And becoming a patient taught Saez-Rodriguez that you need more information to know which drug you should take. Before his diagnosis, he used to describe disease in broad terms at the population level. But now he wants to get down to the detail of a single individual and where they fit into the data. That's what led him to create the IgAN Atlas, which uses big data sets to find more targeted treatments. Researchers can compare multiple organs from multiple patients across their tissues, genes, proteins, microbes, and any other relevant players to get the full picture of disease. By compiling huge sets of molecular data, the Atlas has helped identify key cells that scar the kidneys, map the distribution of different immune cells in the kidneys, and even find a gene that could be at the root of the weird inflammation that's so problematic in IgAN cases. And those are just a few examples of the ways big data is tackling this disease. Overall, the atlas has compiled 24 clinical trials that are being conducted right now. And Saez-Rodriguez put his money where his mouth is, because he's enrolled in one of them. Sometimes the career you built before being diagnosed can help you work toward treatments. Other times, it's the reason you need a treatment in the first place. Susan Michaelis was a pilot. Not what you probably imagined when I first described scientists who study their own conditions, but it's what set her on her research journey. In 1997, after 3 years as a commercial pilot, Michaelis landed her plane and collapsed. No one had any explanation for what happened to her, but some other people in the industry seemed to be experiencing similar things. So she set off to study what was going on. Her PhD investigated the flight safety and health implications of exposure to contaminated air in aircraft. Yep, through her studies, she figured out what had happened to her. It's called aerotoxic syndrome. Michaelis learned that toxic fumes occasionally leak into plane cabins from their jet engines, even on new planes. This has affected more than 100 flight attendants and pilots over the last 20 years, and the reports are only growing. Now, I don't know if this will make you feel better or worse, but it's much more frequently reported in pilots and crew than in passengers. So technically anyone who flies could be at risk, but the risk varies. That risk comes from something called bleed air. Basically, all airplane air goes through the engine by design. Unless you're on the Boeing 787, that's the only plane that doesn't send air through the engine. Usually, bleed air is filtered, but oil and hydraulic fluid can seep into really hot places like a plane's engine and power units. Then that stuff can vaporize and release dangerous stuff like carbon monoxide, organophosphates, and formaldehyde into your breathing air. Since planes are literally designed in a way that could introduce this risk, they have seals to minimize that leakage, but they don't completely prevent it. So normal operation will produce some contamination in the air that you breathe on a plane. Most of it comes from times when the plane uses a lot of power or changes pressure, like during taxi or takeoff. It isn't the kind of thing you usually see, and you become acclimated to the smell quickly. So it's easy to miss, but for some people like Michaelis, it's really toxic. Different people have different genetic susceptibility to the compounds in these fumes, which is probably why not everyone suffers the most extreme version of aerotoxic syndrome. Some people don't report any effects at all, but for those who do feel symptoms, they can range from short-term dizziness and fatigue to chronic lung and heart damage. And sometimes the consequences can be far worse. Michaelis' doctors believe that toxic fumes in bleed air caused her breast cancer. After all, there are contaminants in the fumes that are suspected to be carcinogenic, and aircrew have higher rates of cancer than the rest of us. What's worse, Michaelis' breast cancer was a kind known as lobular. It's different from the more common ductal breast cancer because it doesn't form a lump, so regular screening may report cancer-free status when there's actually a serious problem growing. And last year, lobular breast cancer took Michaelis' life. But not before she brought attention to aerotoxic syndrome and lobular breast cancer through academic publications and campaigns geared toward the public. Thanks in large part to her work, the airline industry is working on several innovations to prevent this from happening to others. Bleed-free engine designs and air quality sensors are the future of plane technology. Ultimately, these scientists may have entered into their area of research because they wanted to understand their own conditions and find treatments. But their work helps everyone affected by those illnesses, whether it's a rare disease or one that just doesn't have much money behind it. Lots of challenges are being tackled by people who have a personal interest in spearheading those efforts. And they are literally saving lives. So it's a good thing they got interested in themselves.